And we continue Meeting C++ 2025 with this talk, which I'm looking forward to. The Code is Documentation Enough by Tina Ulbrich. Tina, I'm really excited to see what you have to say. So take it away.
Okay, thank you, Jens. Yeah, we'll jump right into the talk. Thanks for coming to the talk, The Code is Documentation Enough. I attempted to give a comprehensive overview of how to write expressive code that ideally doesn't need comments to explain what's going on. I will also cover when a comment is needed and how a good one can look like. I understand that this can be an opinionated topic, so I want to share some best practices without being too dogmatic. So why do we want to write expressive code in the first place? For guidance, we can look into the C++ core guidelines. The C++ core guidelines provide guidelines for writing so-called modern C++, that is C++ 11 and newer. The guidelines focus on safety, simplicity, and efficiency. They emphasize high-level issues like interfaces, resource and memory management, concurrency, and rather than style details. These rules are meant to guide architecture and be tool supported and gradually introduced into code bases. There are ongoing updates and community feedback. So let's look into a specific guideline. This is P1, express ideas directly in code. Reason. Compilers don't read comments or design documents, and neither do many programmers consistently. That is, what is expressed in code has defined semantics and can, in principle, be checked by compilers and other tools. We also get an example. Here we have a class that represents a date and two functions. Here's how the core guidelines explain this example. The first declaration of month is explicit about returning a month and about not modifying the state of the date object. Note that this function is const. The second version leaves the reader guessing and opens more possibilities for uncaught bugs. This guideline is quite long, and there are also two more examples. One is about using standard library features, and the other one is about using strong types. There are also some more guidelines that fall into the category of expressive code. They are all in the philosophy section of the core guidelines. I won't go into the details of the guidelines here, but we will touch on almost all of them during the talk. If you want to read the guidelines yourself, I have linked them in this slide deck here. But even if you don't follow the core guidelines, you most likely work within a team. You need to read other people's code and they have to read yours. Or worse, you have to read your own. So it's a good idea anyways to write expressive code. Because the longer you need to understand the code, the longer a bug fix or a new feature takes. In the worst case, no one knows what the existing code is doing. This can develop into a maintenance nightmare. We will look into many different aspects of how to write expressive code, starting with variables, functions, strong types, organizing code, unit tests, language features, and comments. And yes, comments are a part of this conversation. So let's start with variable names. Good variable names are sometimes obvious, sometimes not so much. Finding good names for variables makes the code easier to read and easier to change. So let's look at an example. This is a very well-known algorithm. I'm not sure if you already see what algorithm this is. So this is a weighted average. But nothing in this function is helpful to the reader. You don't even know which of the inputs is the values and which one is the weights. So let's change that. First, we give the inputs and the sums proper names. Just by choosing descriptive names for your variables, the code gets more readable in an instance. It's way easier to reason about it and find potential bugs. Just to very quickly go over the algorithm. For the weighted average, the values need to be multiplied with their corresponding weights. The product of those two values need to be summed up. And also we need the sum of all of the weights. The weighted average is then the sum of the product and values of the product of values and weights divided by the sum of the weights. Variable names can also be used to make parts of the code more readable. If you look at this code here, this is still an implementation of the weighted average. But this time, instead of using a raw loop, I used range algorithms and views. If you know how to read the standard library, you know how to read this. A fold left with a std plus will sum up all the values in the given range. Zip transform will apply the given function to its input ranges. But even if you know how to read this, it might be still hard to understand what is going on. In this case, giving the different stages of the algorithm names can help with readability. Now the different stages of this algorithm got distinct names. The zip transform and the two fold left got their own variable with a descriptive name. Even if you don't know how to read the standard algorithm in views, you can now understand what is going on in this function. It's not always obvious that a variable name might not be fitting very well. If we look at this example, we can see some issues. The zip transform pipeline got the name result, which is somehow correct, but it tells you nothing about what is behind this variable. So let's fix this. Let's rename result to a product of values and weights. Although quite long, this name tells you what the variable actually holds when it gets evaluated. Now we look at the lambda in the transform view. The parameter in the lambda is called element, which is a name that is often used when you want or need to be more generic. So it is short for element. But in this case, it doesn't have to be generic, and it also can be misleading, as element is grammatically singular, but the parameter is actually a tuple of values and weights. Therefore, the name should reflect this. A common pattern to use is to name the variable after what is in the tuple. The right order here is also important. So value and weight reflects the values of the tuple. If we would call it weights and values, it would be confusing. You can avoid the naming issue here altogether by getting rid of the lambda and use std multiplies. And this can even be more simplified by using a zip transform, which you saw in the examples before. And here are some best practices for how to name variables. You should use words instead of abbreviations when possible. Sometimes it makes sense to use abbreviations, but only if they are well known or understandable in the context of the function. See if the names are understandable in the current context. If you have a class called user, it is totally okay to refer to username just as name, as we are within the user context. Outside of this context, there might exist more names, so then it will be important to include the context of the variable by calling it username, for example. The name should not have redundancies. In user.username, the second user is redundant and it should be shortened to user.name. The variable names should be consistent in language and style. That doesn't mean you cannot have different styles within your code. For example, variable and function names can all be snake case, and type names can be Pascal case. As long as you're consistent with it, you can use and mix multiple styles. Prefer specific names over general ones. While data is technically correct, it is often too broad. Use a name that describes the data, like customer records. And try to be specific but not overly so. Variable that holds the number of users in the database is very descriptive, but it's also too long. So user count would be enough here. Now we move on to functions. As already shown, you want your code to be expressive. This also applies to functions. And we will look into some best practices when it comes to how to name functions. The same approach for the function applies as for the variable names. But while the variable name tells you what the variable holds, the function name tells you what the function does. It is related, but there are differences. So let's look at this class here. This is a very, very simplified model of a banking account. We can create a new account by passing in the account holder's name. The account holds then the name, a balance, and a vector of transactions. Now we add some member functions. These functions are all called balance, but they all do something different. Can you figure out what the function does based on the parameters and return types? Well, sure, maybe in this case, but there are other cases where it might not be as clear. So for functions, naming should describe what the function does. The first function returns a balance. A common name for this is get. The next function sets a new balance. Whether or not this is a good idea to do this is not part of this discussion now, but to set a value, we usually use the word set. And the last function updates the balance by adding a new transaction. So we should call the function update balance. Functions should have one clear purpose. If possible, avoid side effects. Functions should either return something or change something internally. Doing both at the same time can lead to confusion and surprise side effects. Now, what about the valid function? It doesn't say what it is validating, so we should add that information to the function name. For functions that return a bool, it is custom to use verbs like is, has, or can. Also, function names should be short and to the point. Try to avoid overly long names, like validate balance by summing up all of the transactions to check if it matches the stored balance. This is too long and it makes the code hard to read. If you have trouble finding a good name for your function, consider if the function maybe is doing too much at once. When that is the case, split the function into multiple functions and see if you can give the individual step a designated name. So, and here are some best practices for how to name functions. For functions, use verb and object to describe what the function is doing, like calculate user ID or get username. Functions that return a pool typically have prefixes like is, has, can, or should. Side effects of the functions should be named, like update some member variable. Be consistent and use the same wording for the same things, like always use get for a function that returns a value from a member variable. Keep it concise, like do calculate function is just calculate. Oh, and also be consistent in language and style, the same as with the variable names. And lastly, use domain language. While adjust total price by factor is technically correct, it describes what the function does, and apply discount is easier to understand when considering the domain. So now we will move on to the topic of strong types. C++ is a typed language compared to, for example, JavaScript. But just because it is typed doesn't mean it is strongly typed. When we look at this function, everything looks like it's properly named. But if you look closely, you have no information about the units that are used here. Is distance in kilometer or feet? Is time in minutes or seconds? It might be the intention to make this a generic function to calculate the speed, but if it's not meant to be generic, it can not only lead to hard to read code at the calling side, but it can also lead to errors. So what does the calling side look like? So here we have no information about the units either. So we should try to add some information to this. Well, now at least the variable name is a little bit more descriptive. This is a little bit better, although it's quite long. But there's a second issue here. And just by reading how this function is called, you don't know what is the distance and what is the time. Furthermore, the code compiles completely fine when you switch the arguments. So this is not just a readability issue, but it can also lead to errors. To prevent errors like this, we have several options that would also increase readability. The first option is to encapsulate the inputs in a struct. You typically do this when your function has lots of inputs of the same data type. Like imagine 10 inputs of the same data type. This can get confusing quite fast and lead to errors when the order of the arguments is wrong. You can then use structured bindings to deconstruct the struct if you want to, or if it increases readability. You might find this more readable or not. This is literally up to taste. So what do you gain by using a struct? You can now use designated initializers when calling the function. Now you can see clearly at the calling side which parameter is the distance and which is the time. It makes it easier to read and harder to get wrong. This is one way of making parameters more obvious and easier to use. But there are more ways of achieving this. Let's walk away from using a struct for a bit. Let's say we don't want a generic function. We need the inputs in a certain unit. For the distance, we need meters, and for the time, we need seconds. So the speed would then be meters per second. When you want to improve readability of functions, you can use type defs for this. In this case, all of the underlying types are double. And now we have named types that we can use in our function. When calling this function, we didn't improve anything at the first glance. And although it is not needed to compile, now we can add our type defs to the function call. Now we also made a significant improvement in readability on the calling side. While this is a lightweight solution, it has one major downside. Type defs are just aliases, not real types. That means I can write something like this and it will compile without any issues. So while aliases are a lightweight solution to improve readability, they are not type safe. But we do have some type safe options. We can define a type safe type ourselves by using a struct. This struct then is the strong type. We do that for all of the types that we want to use, here meter, second, and meters per second. Now the function can use these structs as input, and you will have to provide an instance for that struct to make it compile. That means it is no longer possible to switch the parameters around like we saw with the alias solution. But it comes with its own challenges. You might be asking how the compiler knows what to do with this division here. There are many different ways of implementing the same thing. In this case, we could call .value for the distance and time and make use of the built-in division operator for doubles. This is one way of implementing the division. Or we can provide another function to perform the division or overload the division operator. And this is what I did here. And by overloading the operator, the usage becomes more natural and readable. But only if the overloaded operator doesn't contain any surprising implementation. So you have to be careful with that. This can look like a huge downside as you have to provide a lot more code to do the same thing as with the built-in types. But this is also exactly why we want this in some cases. Imagine the unit case here. It doesn't make any sense to add a time to a distance and it can lead to errors. So by using strong types, we can prevent that from happening during compile time. Other operations do make sense, like the division, and therefore we can provide specialized code for it. And you can define what is allowed with your type and what is not. And this is the real strength of the strong type. I know a lot of people are already screaming in their heads, use a units library. And of course, they're right. There are different libraries for physical units. I'm going to use MP units by Mateusz Pusch. The advantages of a units library are that all units are supported without you having to define a thing yourself. Also, all of the operators are taken care of. And what is very important for physical units as well, the conversion between the units. This example now uses MP units. You don't have to define the result type but if you want to give it a name, you can. Otherwise, the result will just be a templated type. But if you never need the result type for anything, you can just use auto and not deal with it. When calling the function, we create the correct types by using the unit symbols. So using strong types does not only make your code safer, but also more expressive. While physical units are a perfect use case for strong types, there are more. They are used when security is a concern or when there are several parameters that have the same underlying type. I showed you a simple way of defining your own strong types, but you don't have to reinvent the wheel here, as there are many handy libraries that you can use for this. Some of them are on the slide here, but I'm sure there are even more libraries that you can choose from. And there are also at least 3 specialized libraries for physical units. I highly recommend to use one of them if you're dealing with physical units. So to summarize, strong types have a lot of benefits. They prevent mixing up parameters when used instead of plain old data types. These are checks that run at compile time, which is the place where we want to catch the errors early. The interface becomes more readable, and you can not just see from the names, but also from the types what the function does. The types themselves can also have built-in checks. For example, a percentage type can check in its constructor that the value is between 0 and 100. There are less implicit conversions in functions. Built-in types can assignedly convert into other types, which can lead to bugs. And again, there are lots of libraries that you can use when you want to define your own strong types. And I, again, particularly recommend to use a units library when you have to deal with physical units. Mateusz Pusch also has a great series of lightning talks highlighting various bugs that are caused by unit errors. So now we have talked a lot about how to name things, but there are other things that are also important when we are trying to write readable code. And one of them is how the code is organized. In general, we want to avoid spaghetti code. That is code where a lot or even everything is done in one large function. This is not just very hard to read, but also hard to debug, especially when variables are initialized all over the function and changed throughout. It is very hard to track how they change, and code like this is very bug prone. So consider this code. First, finding a good name for this function is not easy because the function is doing so much. To refactor this, it is advised to move the individual calculations into their own function. Sometimes you can find a particular pattern in the code, which is a comment describing what the following code does. We can use this pattern to divide the function into smaller individual functions, as these comments not only indicate where a new algorithm starts, but it also already gives it a name. Now we have designated functions to calculate the different statistics. This has many advantages, like improved readability and reusability of the functions. Now they can be used elsewhere in the code when they are needed. Also, they are now better testable as you can test them individually. With small functions, you can oversee the consequences of changes more easily and therefore enable safer code changes. There are lots of coding guidelines when it comes to how to write code. They might be seen as irksome, but they are meant to improve readability, testability, and reduce bugs. One common guideline is to restrict the number of lines a function can have. There are a lot of different guidelines regarding the number of lines in the code. Some say up to 100 is fine. Others say more than 5 already needs refactoring. I see these numbers as extremes of a spectrum. I personally think around 20 lines is fine. And with the above refactoring, we reached that goal. A line limit can be a guideline or a hard rule that has to be enforced. When moving code to their own functions, you should also keep in mind to keep one layer of abstraction. If you look at this code here, you see that there are two functions that describe what they are doing, calculating the mean and calculate the standard deviation. This is one layer of abstraction. The calculation of the variance describes how it is calculated, and this is another layer of abstraction. And mixing these layers can lead to less readability. And what we should do is to move the calculation of the variance into its own function. Now we are keeping one layer of abstraction in this function. It is more readable, and as I said before, the calculate variance function now can be used elsewhere and can be tested individually. Another common guideline is to restrict the number of parameters a function can have. This is to prevent the function from doing too much. It is common to view more than 3 or 4 parameters as a code smell. So consider this function, which takes 4 doubles that represents 2 points. For readability reasons and also to reduce the number of parameters, we can define a struct called point that we can use in this function. It is a very common strategy when dealing with lots of inputs or large parameter sets. It also bundles parameters together that belong together. For functions that use lots of booleans as input, it is advised to use enums instead. So you can see directly which settings are used. If you look at this example here, in the first line we're using booleans, and you don't see which settings were set. In the second line, you can see exactly which settings are used. You should also avoid deeply nested functions. Coding guidelines typically say to not have more than 2 or 3 nested scopes. This is because code can be very hard to read when it contains a lot of brackets and indentations. You quickly lose the overview of the function, and bugs are more likely, for example, being in the wrong else block or adding a break at the wrong position. To avoid this, consider early returns. You can test the conditions of the parameters at the beginning of the function and react accordingly. And here are some other best practices when you aim to improve readability and therefore reduce bugs. Some teams set a line limit for their function. There's a lot of debate around the maximum number of lines a function should have, and a reasonable line limit can help keep the scope of the function small. Most coding guidelines say to not use more than 3 parameters in a function, and using more as an indicator that the function is doing too much. You can always encapsulate parameters in a struct if needed. The depth of nested scopes should not be more than 2 or 3 layers, and consider early returns. We should also keep one level of abstraction, as it also improves readability and testability. And I didn't show them here, but they are refactoring tools and tools that enforce coding guidelines that you can use. There are way more guidelines that I can show here in this talk. And for guidance, you can Google coding guidelines of large companies, as they can be typically found online. Moving on to the topic of unit tests. I hope I don't need to convince you that unit tests are a good idea anyways, for numerous reasons. One reason is that it also is documentation of how the code is used and which edge cases and boundaries exist. For why and how to unit test, I'd like to refer you to Kevin Henney. He talks a lot about testing and programming with guts. That is, good unit test is one talk that I remember quite well. Unit tests also allow you to find errors early, enable safe code changes and refactoring by checking for regressions, improve trust in the code, and also document the behavior of the code. So now that we're all on board with writing unit tests, let's see how to write a good one that documents what the function is doing. It doesn't matter which testing framework you're using, it is only important that you're using one. Test functions need to explain what they are testing. So when you read the code and when the test fails, you know exactly what is going on. There are different patterns for naming tests. Let's say we want to test that the mean function throws an exception when the input is empty. There are common patterns for naming the tests. One test pattern name is method name, state under test, and expected behavior. In our case, that would be calculate mean, empty input, throws exception. Another common pattern is given when then, given empty input when calculating mean, then throws exception. I also found this one, should expected behavior when state. That would be should throw exception when input is empty. And there's also more of a descriptive sentence like test calculate mean throws exception for empty input. This is what I typically use because it feels a little bit more natural. And I probably also left out some naming patterns. If you decide to use a naming pattern or not is up to your team. It can help making the tests more consistent, but it can also sometimes be hard to stick to a certain pattern for all of the test cases. I also want to emphasize that it doesn't matter if you use a pattern or not. The most important thing is that the test name is clear and that you know exactly what the test is actually testing. So let's go back to testing the mean function. A first test case should be that the mean can be calculated when the input is not empty. So let's start with that. A good unit test only tests one thing at a time. It also tells you what is expected from the function with the given input. So just by looking at the unit test, you can see what the function or class does and how to use it and what corner cases there are. For calculating the mean, we should also consider what the function should do when the input is empty. It could throw an exception, return an error code, or even just return 0. What is implemented can be determined by good unit tests. So if someone changes the behavior of this function, the test will also detect it. Writing good unit tests is good practice in any case, and if they are well written, they can tell the reader a lot about the implementation of the function or class and how it is supposed to be used. We're moving on to language features. Language features can also help not just with safety, but also they can tell you a lot about the code. You should know your standard library. I know the standard library is not a language feature, but it is part of the language, and a C++ developer should know the C++ standard library. The same goes for all the other languages. The standard library is tested and stable. Of course, it can contain bugs like every other software, but it's far more likely that you introduce bugs yourself when you implement your own functions. Using the standard library functions also mean that you don't have to write and maintain those functions yourself. Using the standard library features is aimed to make the code more readable. It provides familiar and consistent solutions. Developers don't need to understand custom implementations and can immediately understand patterns and meaning, making the code easier to read, maintain, and share across teams. I can only highlight a few features in this talk here. So you might have noticed that I used const throughout all of my code examples, and that is on purpose. Using const everywhere when possible is advised and tells you a lot about the code. Const parameters will not change in the function. In fact, it would be a code smell if these parameters were not const. Same for the local variables. I would instantly recognize if one of these variables would be non-const, and I would wonder why. Why would they even change in this calculation? I know it is not necessary, but I also use const in the header files for documentation reasons. We should also prefer to write pure functions that are functions that have constant input and return a value without having any side effects. But sometimes we cannot avoid an out parameter, for example, to prevent a copy from a non-movable data structure. In that case, a non-const reference of a parameter conveys the information that we're dealing with an out parameter. This is why you should be consistent with the usage of const. If you're consistent, it reduces the mental overload of tracking changes of the variables and trying to figure out the interface. I am personally also a huge fan of concepts, and with concepts you can perform compile time validations of template parameters. This does not just make the code safer, but also more readable. You can now see directly in the interface which types are supported by the function. Concepts are also made the code can also make the code more readable, especially compared to enable if. On the slide here, you see 3 ways of using the range concept random access range. The first style you typically use when you perform more complex validations, like checking if the range is random access and the value type is floating point. The second type is typically used when you want to apply one check, but you also need the template type in the function. And the third style is typically used when you want to apply one check, but you don't need the template type anymore in the function. In my opinion, this is clearly an improvement on readability and also safety. If you have constraints on your template parameters, use concepts to check them. Lots of functions also have pre and post conditions. Currently, they are most likely to be ensured by if clauses, asserts, or macros that implement contract-like features. Preconditions are most likely be tested at the beginning of the function, and therefore, by looking into the function itself, you can see these preconditions at the beginning of those functions. Postconditions would typically be checked at the end of the function or at the calling side. Currently, most code probably uses if statements or asserts for that, but there are also libraries that you can use. For example, expects and ensures are macros from the guideline support library. And these macros effectively implement contracts in the program and will by default terminate if the pre or post conditions are violated. And with C++26, we will also get contract support. Pre and post conditions will probably look something like this with contracts. The big advantage of contracts over the previous implementation is that contracts can be put into the header file. Therefore, humans, compilers, IDEs, and static analysis tools can read them without having to access the implementation. I am far from being an expert on contracts, but Timo Dumle is. So I recommend to check out his talks about contracts, like this one from this year's ACCU. So just to quickly summarize this chapter, the standard library is part of the language, and software developers should know their standard library. The standard library provides tested and efficient functionality, and it saves you time and support to use it instead of implementing your own version of it. And what I didn't mention here are features like the algorithm header, numeric library, ranges, chrono, and so on. And they all greatly improve readability in the code. There's only very, very, very few instances where const is not advised, but otherwise make const what you can make const. It prevents the accidental change of the variables, and it also documents to the reader that the variables will not change, or that the member function of a class will not change any of its members. Concepts are used for compile time checks of template parameters. It makes clear which types are supported by the function, and it greatly improves readability, especially compared to enable if. And we will get contracts with C++26. And these can be used to check pre and post conditions of functions at runtime. And I'm very sorry if I didn't mention your favorite language feature here. So what if you use all of the above techniques and all of the best practices, but your code still does something that needs more documentation? Well, then you should write a comment. In general, a comment should describe what the code, not what the code does, but why it is needed. So here are some examples for what can be considered a bad comment. In the first example, we see some redundant documentation. You can clearly see what is going on in the code, and there is no need to further explain it. In the next example, you see a comment that is outdated. At some point, the code was changed from the mean to using a median, and the comment was forgotten. This can be confusing because you don't know if the comment is what is supposed to be happening in the code or if the code is correct. In the next example, we have a to-do in the code. In my team, we have a rule that we don't leave any to-dos in the code. We should fix them right away if possible. And if it cannot be fixed currently, rather explain in the comment why it is implemented like this, and then add an issue to your issues tracker so you can find this again and it will not be forgotten. And jokes and insider comments might be fun, but they don't add any value to the code and it can be confusing. But there are also places where a comment is needed and it is actually valuable. In the first example, the comment explains why stable sort is used instead of another sorting algorithm. Without the comment, it might not be obvious why it is needed and it may be changed accidentally. Next, there's a comment that documents a workaround because of a bug. This is also important to document so that you can come back and fix this when the bug is fixed. And also so that no one changes it accidentally. This also needs a corresponding item in your issues tracker. Some internal logic might not be obvious, so here a comment can be helpful. And if you're using static analysis tools, you sometimes need to disable warnings or issues. And here the comment should not just disable the issues, but it should also describe why the warning was disabled. And also, not every code is easy to understand. For example, we sometimes have complex calculations. Here a comment explaining what the mathematics, here a comment that explains the mathematics or a link to external documentation can be very helpful in understanding the code. I took this one from Python's SciPy library and I have still no idea what a Henkel matrix is. Sometimes we also specialize code. We take generic code that support lots of use cases, but we only implement what we need. So a comment explaining what the source of the code is and how it was specialized to a certain use case might be very helpful. And lastly, external APIs are often documented extensively. And again, I took this from Python's NumPy library. As you can see, I'm not for not using any comments ever, but if you use them, make them good, correct, and useful, and also update them when needed. Now, lastly, how can you ensure that the code is actually readable and adheres to the coding guidelines? There are tools that check coding guidelines like ClangTidy, ReSharper C++, or SonarQube. Other tools ensure that the code has the same formatting throughout, like Clang format. And consistency in the formatting also improves readability. There are no tools that I know of that check readability of the code. So this is still a human task. Code reviews are a good place to do this, and there are also different ways of doing code reviews. If you want to ensure readability, you can consider doing code reviews where one reviewer tries to read and understand the code by themselves, instead of getting it explained by the author of the code. If the reviewer cannot understand what is going on, then it is an indicator that something needs to be changed in the code, or even if a comment might be useful. Another useful tool is also pair programming. Talking to someone else, discussing how to implement something also helps with the end result being more understandable. But I still would want to get a review from someone outside of the pair. So, to summarize, giving your variables and functions clear names that are descriptive but not overly long will tell the reader what is going on in the code without using any comments. Using strong types are a good idea for many reasons, but they also document the code even further by including concrete information on the used types. By bringing the code into a good structure, you can also improve readability. Tools can help enforce coding guidelines. Unit tests are best practices anyways, but they also document how the code is supposed to be used. For unit tests to function as documentation, they need to have clear descriptions of what they are testing. Also, all paths need to be tested and not just the happy path. Using language features like concepts, contracts, or even const, you can express clear intent of the code. And sometimes a comment is useful. I showed you some examples for that. Use common sense and determine if and when to write a comment. I personally don't believe in extremes. Not everything needs a comment, but also sometimes comments can be really useful. And lastly, these things can hardly be enforced by tools. As I said, I don't think there are tools that check for readability, but there are some tools that are checking for coding guidelines and applying formatting. To ensure that the code is actually readable, only a human can really determine. And during code review is a good time for that. And lastly, be consistent, but maybe not too dogmatic. Common sense applies to all of these guidelines. So that is it. Thank you. Do you have any questions?
Thank you, Tina. Let's see if our audience for this recording has any questions. Generally, very good talk, and I really like it that you know. I was curious about what topics you'd be addressing, and that was really a good talk. Thank you for that. And recently, just maybe also like spawned through your talk, I just had some thoughts on that. The criticism that a code change doesn't change the comment is also true for the names we have in the code, right? So a function name or a variable name, and so that's always good to be explicit and to, name things, but also be aware that maybe the function name is not directly telling you what it does.
Yeah. It can happen very quickly, like choosing or switching from mean to median, and your local variable still is called mean of something. Yeah, that can happen very quickly.
And I was wondering, and then I saw that you used the library, and I was like, you probably didn't misspell it, but there's meter and there's metre.
Yeah.
And are they the same?
Yeah, they are the same. The spelling I used is the British spelling, and I used it throughout this talk or throughout of my slides because MP Units is using the British spelling. And meter, like the other spelling, is the American spelling.
That's interesting. It's also in German meter, so.
Yeah.
But yeah, of course, if you're using the library type, then that's what you have to use. Anyways, very nice talk, and there's a common another question, but other than that, I think it was a very good talk, and thank you for your time, and see you then online in 4 weeks when we're starting the conference. And actually, your talk will be the second one going live at the conference in the online track. And so, thank you for your talk.
Thank you.